Hi everybody, it's Jeanette and I am here to cover Factorial Designs covering Chapter 9. So this is the last chapter in this module. Hopefully it'll give you some insight for that final paper that you're doing. We have already talked about an IV, and with an IV we have different levels or conditions that we reference. In an experimental design, one of those levels represents the treatment for the experimental group, and the other represents the control group who's not exposed to the treatment. So, or they're exposed to a placebo. So, when we talk about an experiment with only one IV and only 2 levels, you should know, although it's conceptually easy to understand and we think of it as a fairly common type of design, it actually doesn't give us as much information as is usually occurring in the real world. So it only looks at kind of linear relationships. It doesn't look like a changing trajectory. So if we actually build in different levels or different conditions, then we can actually see, is there a nonlinear relationship that exists? And you can only see that if you have more than one level of an experimental variable or more than 2 levels or conditions in a study. So when we talk about increasing levels, we can see whether or not the relationship is monotonic or non-monotonic. When it is monotonic, a positive linear relationship exists between the IV and the DV. We see it just increasing in one direction. But when it's non-monotonic, we can see a curvilinear relationship or a shift in the incline changing. We can only detect that if we have more than 2 levels of an IV. Factorial designs can be used when we include more than 2 or more IVs, and those IVs are now referred to as what we call factors. And you can have different levels or different numbers of conditions or levels for each factor or each IV. So one IV can have 2 factors or 2 levels or 2 conditions, and the other IV or factor can have 3 conditions or 3 levels. So in a factorial design, all levels of each independent variable are combined with all the other levels of the other independent variable. So we're looking at that relationship between those 2 factors. Like, let's take, for instance, if we wanted to look at the effects of exercise and the frequency of exercise on mood. So our first independent variable or factor would be amount of exercise, and we'd have 2 groups, a control group that doesn't exercise and an exercise group or an experimental group that does. Then our second IV is we're going to have 2 experimental groups, one that exercises 3 days per week and one that exercises 2 days per week. So the frequency of exercise and the type of exercise are variables. So I'm looking at our exercise group when we see them 3 days a week, our exercise group when we see them 2 days a week, our no exercise 3 days a week, and our no exercise 2 days a week. So I'm measuring mood every time I see them, and I want to see how that exercise or no exercise changes mood based on frequency. Another study is looking at sociability and food consumption. So if peers are eating food, does it influence how much food I'm willing to eat or our participants are willing to eat? And does it matter whether they're sociable or not sociable? So you can have a sociable peer that is not eating as much, and how does that influence how much I eat as the participant? You can have a sociable that is eating a lot, like a bowl of M&Ms, and they're eating a lot. How much does that influence how I eat? A non-sociable peer that's not eating a lot, and then a non-sociable that is eating a lot. And I can see across those 4 conditions, how is that impacting my eating? How is my eating being influenced by the sociability of my peer? and or the food intake of my peer. Am I more willing to eat with non-sociable than sociable? Am I more willing to eat with low intake or high intake peers? I like peers that eat with me, just for the record. Anyway, so a factorial design is when we include multiple IVs. It's our most common approach, really, to research. Very rarely do we only look at one single IV. And as I mentioned, each level of the IV, so in this case, cell phone use, no or yes. In this case, time of day, nighttime or daytime. Each level of this IV, so no is with daytime and nighttime, yes is with daytime and nighttime, daytime is with no and yes, and nighttime is with no and yes. So each level of one independent variable is combined with each level of the other independent variable. So however many levels I have in the variables, I can multiply those out to determine how many cells or separate conditions I have for the study. So variables are represented in a matrix, just like this, where one variable, if it has two conditions, the other variable of time of day has two conditions. 2 by 2 equals 2 times 2 equals 4. So I have 4 separate levels and conditions. So the variables are represented as a column or a row. Each condition of the variable is a column or a row. And those columns and rows intersect to create levels or conditions. And so each of the cells represents one of those respective levels or conditions. Hold on, my bunny's escaping. Bun. Don't go out there. Okay, sorry. Anyway, so all possible conditions in this study are represented in that matrix. When you have a factorial design, we write it out similar to a math equation. So I literally call it a 2 by 2, or a 2 by 3, or a 2 by 2 by 2, or a 2 by 3 by 3. And the number of numbers in that equation tells me how many factors I have or how many IVs I have. The number itself tells me how many conditions are in that IV. So just the presence of a number tells me that represents an IV. And then the number itself tells me how many conditions are in that IV. So if I have 3 IVs and it's a 2 by 2 by 2, I can multiply 2 times 2 is 4, times 2 is 8, and a 2 by 2 by 2 design results in an 8-cell matrix. If it's a 2 by 2 by 3, and that's going to be 2 times 2 is 4, times 3 is 12, a 2 by 2 by 3 results in a 12-cell matrix, okay? So again, the equation tells me how many variables I have because each number represents a variable. And then the number itself tells me how many conditions or how many levels in that factor, okay? And so in this particular one, there literally was a study where they had a confederate who was either sociable or non-sociable, so they chatted or they didn't. And they ate a lot of M&Ms or they didn't eat M&Ms, and they really were looking at how that affected the food intake of the participant. And so this is a 2 by 2 because I had 2 independent variables or 2 factors, and each one of them had 2 levels. The first independent variable was sociability, sociable compared to non. The second independent variable was food intake, low versus high. And that resulted in a 2 by 2 design, which can, when I multiply that together, it's going to create a 4-cell matrix. Okay. Here's it represented another way. What this now allows me to do is it allows me to look at the mean effect. So I'm going to have a mean of, I'm counting the number of M&Ms the participant eats. I'm going to have an average number. If I have 20 participants, I'm going to have an average number of 20 participants who were exposed to a sociable confederate and a low food intake. And I'm going to count their number of M&Ms. That's going to give me an average. How many M&Ms did they eat as a whole on average? Then I'm going to get a mean for the group that was exposed to an unsociable confederate who didn't eat a lot. Then I'm going to get a mean for the sociable confederate who ate a lot. And then the unsociable who ate a lot. And then this now becomes my entire, like these are all my scores for all my participants exposed to Confederate. I get what's called a marginal mean for the total number and average of M&Ms that were eaten for all people in the Confederate condition, or in the sociable condition, and then all the people who were exposed to an unsociable, and then all the people who were exposed to low intake, and then all the people who were exposed to high intake. And these create marginal means. So with a 2 by 2, I have a marginal mean for each condition, right? So I have a marginal mean for low, and a marginal mean for high, a marginal mean for sociable or unsociable, and a marginal mean for sociable. Those tell me what's called a main effect. The cellular means, the individual cellular means, I use to analyze the interaction. So when I'm looking at a main effect, my main effect is my research question that relates to one IV, as if the other IV is not even in the study. So what is the effect of the sociability status of my peer on my food intake? Does my food intake change whether I have a sociable peer or a non-sociable peer? That's one research question. My other variable, and the main effect is the answer to that research question. The other variable is now food intake. Does my food intake differ when I'm with a peer that eats more or eats less? And so that's my other research question. So I'm analyzing the main effect of sociability on the participant food intake and the main effect of the peer food intake on the participant food intake. Those two separate research questions for each separate IV produce what's called main effects. So the main effect is the individual effect of each individual IV on the DV, assuming the second IV isn't part of the study. Okay? So it averages all the levels within that IV into one. So we act like the other IV doesn't even exist and it's not broken up into two groups. I'm not looking at differences between low and high. I'm only looking at all the sociable numbers and all the unsociable numbers as just two groups, not four separate groups, okay? The interaction is now looking at, does the effect of the food intake of the peer on my food intake depend on the, so when I'm asking about an interaction, I'm asking, does the effect of IV1 affect the DV? Or does it depend on the condition of IV2? If the answer is it depends, then you have an interaction. So it depends indicates that the effect of IV1 depends on the condition of IV2. So maybe when I'm with a peer that's eating a lot, I might also eat a lot when they're not sociable. But when they're sociable, maybe I don't because I'm too busy talking to them and I can't eat and talk at the same time. So when the effect of one IV, in this case, food intake of my peer, on my food intake, when the effect of food intake on the peer, food intake of the peer on my food intake depends on the other IV, in this case, the level of sociability, I will eat more when they're unsociable and less when they're sociable. Then that means that there's a significant interaction. So the interaction is the combined or interactive effect of the two IVs together on the DV. It's looking at how the effect of one IV varies depending upon the condition or level of the second IV. Interactions are really powerful. They give us a lot more information. They are often the focus of our research. We're not just looking at how one IV in isolation influences us, but rather how we're influenced by this dynamic, complex interaction of multiple factors together. So Whenever you hear "it depends," where the effect of one IV depends on the level or condition of the other IV, that means there was an interaction. If you think about real behavior, right? Like, hey, do you want to go to a movie tonight? Well, it depends. I have an exam, right? So if I have an exam, then no, I don't. If I do, then yeah, sure. Also, who's starring in the movie? If it's one of my faves, then absolutely. If it's somebody I don't care about, then yeah, no, I'll pass, right? Maybe I'll absolutely go even if I have an exam, when it's someone that I love, but when it's someone I don't love, then yeah, I'm not so likely to go, right? Or maybe the opposite. Even if it's someone I love, when I have an exam, I'm not likely to go. So the effect of the star depends on whether I have an exam or not. So that's kind of the real world. And real world behaviors often are influenced by an interaction between variables. So factorial designs allow us to study separate individual effects of IVs, which we call main effects, and interactive effects, that combined complex dynamic between two or more variables, okay? When we're looking at, well, what are the answers to our research questions? Graphs are particularly helpful in a in a factorial design. We typically will look at the vertical axis as the y-axis as our dV, right? And then the IV is on the horizontal axis. If we're doing a bar graph, then you're going to have different colored bars for one condition, and the other color for a different condition. And then they're going to be grouped separately. So in this case, here's sociable grouped and here's unsociable. But here's the green is the low food intake and the orange is the high food intake. So I can compare and see, okay, well, the effect of the Confederate on my food intake, I ate the most when they were unsociable, right? But when they were eating a lot. So the effect of the sociability depended on their food intake. If they were eating a lot and unsociable, then I ate more. But if they weren't eating a lot and they were unsociable, I didn't eat more, right? So that's looking at an interactive effect, where the effect of one IV depends on the condition of the other. So their sociability affected me for the high food intake, but not for low food intake, okay? Okay, so when we're talking about factorial designs, they can have either manipulated or non-manipulated variables or some combination thereof. Remember, a manipulated variable is an experimental variable. I decide as the experimenter how I'm dividing up the groups, what level of treatment they're getting, and I'm randomly assigning who's in which group. And for a true experiment, I have to have random assignment, and I, as the researcher, have to manipulate the variable. Well, we can, in fact, have non-experimental variables where we're still comparing dVs between groups, but I'm not manipulating the variable. These now might come in preformed groups, right? I'm not directly creating the groups, right? I might look at sexual assault survivors and non-sexual assault survivors. They come preformed. I might look at gender. They come preformed. I'm not randomly assigning. So therefore, they're non-experimental variables. I didn't directly manipulate them. We can use participant variables. A participant variable is also known as a subject variable or an attribute. So when we look at an attribute or demographic of the participant themselves, like gender, for instance, maybe women participants are going to eat less M&Ms than male participants. That's a subject variable. When an attribute of the participant becomes a focus of a research question, it's what we call a participant variable. Now, keep in mind, we collect demographic data on participants all the time just to describe whether our sample is representative. That doesn't mean it's a variable of interest for the study. It doesn't mean I'm asking a research question about that variable. If you want to build it into your experimental study, it becomes a participant variable. sometimes in a factorial design, not only do you have separate independent variables that you're asking questions about, but your participant variables can also be built into that factorial design, okay? So maybe I want to do a 2 by 2 by 2, and I want to compare the effective sociability status of a peer, food intake of a peer, and I want to compare that on the food intake of the participant, and I want to look at differences between men and women, okay? That's one example. So when we have an independent variable times a participant variable design, that's also, it can be a quasi-experimental design because it's a participant variable that I'm not manipulating. So studies can include both manipulated variables and non-manipulated variables in the same exact group. When you look at factorial designs, we have one main effect. So for every, you have one independent variable and a research question that corresponds to that independent variable. And for every research question, you're studying a main effect. Is there a main effect of IV1 on the DV? Is there a main effect of IV2 on the DV? And you also have one interaction for each two independent variables. So if I'm studying 3 independent variables, I have an interaction between A and B, between B and C, and between A and C, okay? So what that means is my possible research questions and my possible outcomes become exponential. Because I have one research question for every single IV for the main effect, and I have every single interaction has its own research question. So I want to look for, is there a significant main effect of IV1? Is there a significant main effect for IV2? And is there an interaction? Interestingly enough, you can have all 3 insignificant, you can have all 3 significant, you have 1 significant and the other 2 insignificant, and any combination thereof. Graphs can often be good visual tools for you to see right away if there's an interaction. So what you're graphing, the other one you saw, a bar graph, I don't think bar graphs are as good visually to identify an interaction. Line graphs are better because what happens here, you have you're measuring depression, and you have Prozac versus no Prozac groups, and you have people that are in therapy and not in therapy. So our blue is no therapy, Prozac, no therapy, Prozac with therapy had similar scores. Those distances aren't huge, but look at the no Prozac with therapy had significantly lower depression than the no Prozac without therapy. So it seems like therapy was helping even when Prozac wasn't present. When Prozac was present, the therapy didn't make as much of a difference. In this particular circumstance, I'm seeing no therapy and no Prozac depression was high. And I'm seeing in no therapy with Prozac depression was low. And for the therapy, no Prozac depression was low, but with Prozac depression was high. And so either one of these can represent an interaction. This is a spreading interaction. This is a crossover interaction. We'll talk about that in just a second. Okay, so you have 3 results coming out of a factorial design. A main effect, which is looking at the effect of one IV on the DV as if the other IV doesn't exist. So we're averaging across all levels of the second IV. You have one main effect per variable or per factor. And the interaction is looking at the effect of one variable being influenced by the level or condition of a second variable. And so you have one interaction for every 2 IV combinations. And then simple effects, when we're looking at simple effects, we're looking at the effect of each independent variable at each level of the other independent variables. So we're averaging for main effects and looking at marginal means, but for a simple effect, not so, right? We're just looking at the two levels of the effects of IV on verbal test. Simple effects lets us see, is caffeine in introverts, does that have a different effect than caffeine in extroverts, okay? Okay, so I already talked about a spreading interaction. Your book actually gives you bar graphs to show you a spreading interaction. I happen to like the line graphs better because it's more descriptive and visually outlining what's happening. It's literally spreading, right? You don't see that as much on a bar graph, right? In a crossover interaction, see how these flip-flopped, where it went from short, blue was short here, and then tall here, and then tall here, and then short there. Again, visually, a line graph lets us see that a little bit better. So I personally like line graphs better for interactions than bar graphs. Just my thought. Okay, so here we're looking at how can we interpret graphs for main effects. So this is looking at a main effect of A, right? So here, is there a difference between the score in the first condition and the second condition of A? No. See how the line's flat? No. You can look at the scores here and the marginal means. There isn't a difference between 5 and 5. So there was no main effect for B. There's also no main effect for A, because remember, I'm using these marginal means to analyze the main effect for each of the factors separately. So, and there's also no interaction. They're constant, so there's no interaction. Here, I'm looking at, look at B, my marginal means, there's no difference, right? B1 and B2 are right on top of each other, right? But now look at here for A. A1 is way down here and A2 is way up here. So now all of a sudden, there looks like there's a main effect for A, no main effect for B. And when I look at the interaction, no, because notice for A1, it's always lower than A2. For B, it seems like it's always higher. It starts out low and then goes high, low, high. So the pattern doesn't change in these cells. So there's no interaction. Also, the lines aren't crossing, right? They're not spreading and they're not crossing. Here they're crossing. Notice the pattern changes. Low, high, high, low. Low, high, high, low. So the interaction is significant, but no difference in the marginal means. So there's no main effects. Another possible outcome is when I have, look at no difference, so no main effect for A. But here, there is a difference between 7 and 3. Does it reach the threshold of significance? I have to test that statistically, but likely, right? So that's a yes. And then notice how the pattern changes, where we have, you know, for A1, no big deal, but for A2, hold on, for B1 high, but for B2 low. And so the effect of A depends on the condition of B, such that it matters for B1 but not B2, right? So that results in what we call a spreading interaction, okay? So I'm analyzing simple main effects and my overall main effects. So my significant interactions tell me that the level of 1 depends on, or the effective level of IV1 depends on the level of IV2. For simple main effects, I'm just looking at mean differences at each level of the IV rather than collapsing across, right? And for simple main effects, I act as if there's a completely separate experiment. And so I feel like this is repeated a little bit. In a factorial design, you can have independent groups or repeated measures, just like we've talked about between subjects versus within subjects. One variable might be between subjects, are they taking Prozac or not? And then over time, we can look at, how they're doing 1 month, 2 month, and 3 month. And so one might be a repeated measure, one might be an independent measure. If that's the case, that's what we call a mixed factorial design. A fully independent groups design is when there's different people in each condition. So if I go here, I'm saying there's different people in each condition. if I am, if I'm looking at a repeated measures where first the person comes in and they're really, really sociable, then they stop talking. How does my food intake change? Versus if they come in not talking and they become really sociable, right? So I can counterbalance that, where I can say this is repeated, but this is going to be actually between groups design. So I can do any combination thereof. I can do all between groups designs or between subjects. I forgot where we left off. Give me a sec. Here we go. I can have all, my variables can all be independent groups, so both of them independent groups. I can have a repeated groups or repeated measures, so independent measures, repeated measures, a repeated measures where in an independent measures there's different people in each group, and in a repeated measures there's the same people being measured multiple times. So I can have a mixed factorial where I have a one repeated measure and one independent measures variable. Okay. When I assign participants, when I'm talking about an independent groups, notice this is participant number. There's literally participant 1 through 10 is in this group. Participant 11 through 20 is in this group. 21 through 30 in this group, and 31 through 40 in this group. In a repeated measures, it's the same people, 1 through 10 in every single condition. Here's some mixed factor design where in this particular variable, the same 10 participants are in both B1 and B2. And in this particular condition, the same participants. So different participants in the different A's. So that's a between groups variable. And then for B, it's a repeated, it's a within groups variable because it's the same people in both levels. Okay. So when I increase the number of levels in the IV, my matrix gets bigger. It tells me there's more conditions. So if I do a 2 by 2, remember I times those, that tells me it has 4 conditions. A 3 by 2 tells me I have 6 conditions. A 3 by 3 tells me I have 9 conditions, right? So I'm still going to look at the marginal means for each of these to analyze my main effects. And then those simple main effects are going to be used to help me identify the cell differences or the interactions, okay? So this is looking at the effect of task difficulty, hard, or easy, and then anxiety level, low, moderate, or high. So I have 3 measurements for easy tasks, for low, medium, and high anxiety. And for hard tasks, I have low, medium, and hard anxiety. And I'm looking at performance. So if it's a hard task, low anxiety people do better than an easy task. Moderate, they both do a little bit better. High anxiety, they actually do a little bit worse on the hard task for moderate anxiety. And high anxiety, they start to do very poorly on a hard task, but really well on an easy task. Okay, so the effect of the effect of anxiety on performance depends on task difficulty. Okay, so increasing the number of IVs also increases the number of cells because I still have to multiply. 2 times 2 is 4, times 2 is 8, 2 times 2 is 4, times 3 is 12, 2 times 2 is 4, times 2 is 8, times 2 is 16. So for a 2 by 2 by 2, I have 8 cells or 8 conditions. A 2 by 2 by 3, I have 12 conditions. 2 by 2 by 2 by 2, I have 16 conditions. So in a 2 by 2 by 2 mixed factorial design investigating the effects of instruction method, lecture versus discussion, class size, 10 versus 40, and student gender, male versus female, on test performance. So I want to see, do students perform better on the test for lecture versus discussion, for small class or large class, and do male students do better than female students? So because it has 3 separate IVs, I can't just do one simple matrix. I have to actually break it up and conceptualize it as 2 separate 2x2s. It's going to be a 2x2x2, so it's 8 cells. 2x2 is 4 times 2 is 8. And then if I draw it as 2 separate 2x2s, then that gives me my 8 cells. So I can break up gender, and then so this is looking at the small class size, large class size, lecture versus discussion. Okay. And then I still am going to have main effects for lecture, main effects for discussion. It'll be the combined lecture, combined discussion, combined small, combined large, combined male, combined female, and that'll be my main effects. Okay. And then I'm also going to study the interaction of every 2 variables. So I'm going to study the interaction between method and class size, method and gender, class size and gender. So interactions are looking at the possible 2 combinations. You can do a 3-way interaction, not as common, something you'll study maybe in advanced statistics. So your factorial designs become increasingly complex when you have more conditions and when you have more factors or variables, okay? Sometimes we manipulate all the variables and they're all strictly independent variables for a true experimental design. Sometimes we don't. Sometimes some of them aren't manipulated, and that's okay. So it can be a combination thereof. Okay, just some activities for you to practice and for you to determine. Just play with the ones on top, and then when you're ready, glance down to the answers on the bottom. But interpreting experiments and the effects of main effects and interactions. Okay, so have fun with it. Factorial designs are scary, but fun. And so this will be an interesting learning opportunity for you. Let me know if there's any questions. Bye.